When we first learned about entropy, we learned that it had a connection to spontaneity. And in particular, we learned that the second law basically tells us that for entropy changes in the universe for a spontaneous process, that these always have to be greater than or equal to zero. Right now, this is a perfectly good application, is a pretty good indicator for spontaneity, but it's not a very practical one. And the reason I say this is that the delta S of the universe actually depends on contributions not only from the system, which might be the thing that we're measuring very accurately, but also from the surroundings. And what we know in practice is that this delta S for the system can be positive or negative. Either way, it can be overcome by the change of entropy for the surroundings, but this is itself not an indicator unless the system is isolated. Okay, in the case of a system being isolated, then measuring the entropy change for a spontaneous process will always result in that system entropy being greater than or equal to zero. So if we can't rely on the system entropy in all cases, how do we do this? Well, where would this be an issue? Let's imagine that we're looking at a process that takes place under constant temperature and volume. And this is, not an unusual situation. So, but this would refer to a system that is somehow coupled to a reservoir. That's how it maintains a constant temperature. All right, systems don't normally just maintain their temperature all on their own, but because it's coupled to a reservoir, that means it is not isolated. So this is a particular case where we can't just measure the entropy change for a system at constant temperature and assume that it must always increase in a spontaneous process. Now, I should also note that if I have constant volume, and this is a condition that we've encountered before, it tells us that the incremental change in mechanical work, which I'll write as negative p external dv, must go to zero because dv is vanishing. There is no change in the volume. So for all of this, if I want to look at the entropy change or the entropy of the system, remember that I have the definition for that entropy is that it's just the reversible increment of heat change divided by temperature. If I had an irreversible process, however, and that's where we're mostly talking about spontaneous processes, then I'm always going to have this inequality that tells me that the differential change in entropy is always greater than this increment of heat divided by temperature. So how do I handle all this? What can one do to come up with a thermodynamic indicator that depends only on the system for a condition like this, like constant temperature and volume? Well, here's one way we could deal with it. If we have constant volume, okay, so back up here to constant volume, we also know then, since the incremental change in work is zero, that must mean that the differential in internal energy is equal to the incremental change in heat at constant volume. So we now have something that we could substitute into our expression for the entropy that depends on the change in the internal energy. So in this case, if I rearrange this equation, I would get T ds is greater than the incremental change in heat. And now if I bring down du, so we'll make this heat at constant volume, then I have in effect the condition for all of this that T ds is greater than du as a condition for a spontaneous change that takes place under constant temperature and volume. But what does this really mean? Well, what if I rearrange this and say that du minus T ds, so all on one side, that has to be less than zero. All right, but this thing that I've written here, du minus T ds, is really just the differential of a compound function that I can write like this when I'm at constant temperature. So if a constant temperature, then this thing that's here will be the same as the differential of this function. And the differential of that function then must be less than 0. Well, I hope you're recognizing something that's similar to what led up to the definition of enthalpy. But what we have here is we're going to define a new thermodynamic potential, and I'll call it A, and it's equal to U minus Ts. So it's just the stuff in there. And for a spontaneous process, this implies that the differential change in A must always be less than 0. Now I'm going to go ahead and add an equals here, because if it turns out to be a reversible spontaneous change, then it could be equal to 0, but it can never be greater than 0. If it's ever greater than 0, then this would not end up being spontaneous. So what is this thing? Well, we have a name for it. It was devised by Helmholtz back again in the 19th century. We call this the Helmholtz energy. And it is a thermodynamic potential. It has units of energy. Remember, internal energy has units of energy, and the product of temperature and entropy has the units of energy. So this is a new thermodynamic function that has units of energy and has also the property that it's going to always be less than 0. And I should also finally note that all of these quantities relate to the system. So I no longer have to measure the entropy change for the surroundings, because I have now a measure that I can use to apply to a system. All right, so if I have all of this, how can I think of this? I like always to have a graphical way to think of this. Well, let's first go back to entropy. And how would we think about entropy changing for a spontaneous process? Well, if a process is spontaneous, and now I'm talking about the entropy of the universe. Okay, it might start down here, and we know that it has to be greater than 0. The change in that entropy has to be greater than 0 in order for this to be spontaneous. So it means that it's got a net positive slope, and it's going to come up and up and up. And at some point, it's going to slow down, and it will eventually level off. And when it levels off, that indicates that the process has gone as far as it can go. And so we would think of this we would think of this situation up here as an equilibrium for the system. Equilibrium for the system. All right, and it represents the place where now our entropy change goes to 0. All right, so it's no longer going to change. So another way that we could represent this is to draw a picture, and I won't specify what the horizontal coordinate is, but it tells us that entropy changes for the universe are, for a spontaneous process, always must increase, and when they reach a point at which their net change becomes 0, this represents the equilibrium point to the system. So in other words, we are trying to achieve a maximum in order to get to the equilibrium point for this spontaneous change. Okay, once we have reached that equilibrium, then there no longer is any change in the system, spontaneous or otherwise. So how does this Helmholtz energy compare? Well, it's going to be in some sense just the opposite, and it also is going to apply only to a quantity that we measure for the system. So now I'll have the Helmholtz energy for the system, and it always is going to be less than 0 in its change, so it may start up here and gradually work its way down, but it's eventually going to reach a point where it levels off, and at this point the change in the Helmholtz energy becomes 0, and again we have achieved at this point an equilibrium of sorts that represents the end of spontaneous change. So spontaneous change now is marked by this downward arc in the Helmholtz energy, spontaneous change. So if we're to draw a picture like we did over here for entropy, for Helmholtz energy, now what we're looking for is a minimum in the curve for the Helmholtz energy. So Helmholtz energy is plotted along here against some coordinate. When it achieves a minimum where the slope is equal to 0, that's where change stops, so that's where the equilibrium is. So I'll say the equilibrium is a minimum in the Helmholtz energy. And if the Helmholtz energy, if the change in Helmholtz energy is ever greater than zero, it's not going to move toward that minimum. It's going to move in the other direction. So it moves away from its minimum. So this means that Helmholtz energy is actually something we can think of as being almost like a gravitational field, where things always go to, the lowest part of the whole. In Helmholtz energy, they're looking for the minimum in that thermodynamic potential in order to achieve the equilibrium. Now, I'll mention one final thing, and that is that when we consider an expression like this up here, 4a, that allows us to write, for example, that the change in A might be equal to the change in internal energy minus T times the change in entropy. So that means we cannot determine spontaneity from either internal energy or from entropy, only from A. But it does give us some guidelines. For example, if internal energy is less than zero and entropy is greater than zero, then this has to be less than zero. There's no way it can be positive, so it will be a spontaneous change. So let me write that down. du less than zero coupled with d delta S greater than zero means spontaneous change. All right, if delta U was greater than zero and delta S was less than zero, then we would have no possibility of a change. So the opposite would be what happens here. What if one is, let's say delta U is less than zero and delta S is less than zero also? What happens then? Well, here we're going to have a balance between these two. One is driving you toward equilibrium, the other one is driving you away. So it's whichever one has the greater magnitude is going to determine whether you are going to have a spontaneous change at that point or not. Now I'll note that at very low temperatures, the term that predominates is the internal energy. At higher temperatures, the term that predominates is the entropy. So that's another thing that you can look for, is what is the temperature of this process. And if it's at very low temperature, you want to focus on the internal energy. If it's at a much higher temperature, then you may want to focus on the entropy as a guide for whether or not the process will be spontaneous.